these are some of them. Again, some correlations are listed here. So you can see that delta T is correlated as 13.74 Q dot C power 2 by 5 by Z or into Z power minus 5 by 3, correct. So Q dot C 2 by 5 power 5 by 3 into Z power minus 5 by 3. Okay. So this correlation, basically what we have got exactly has the same trend of variation with Z as predicted by the simplified analysis, because since simplified analysis gives some physics of how the variations of these quantities occur with the height, the same trends are also used in the correlations proposed by several people. But in this correlation by Zukowski et al. At 1981, you can see no virtual origin is used. Now, another correlation, okay, involves virtual origin. You can see, and there is a virtual origin also is calculated based upon the heat release rate and this. Hesketh dash has given this. For this delta T, again you can see that Q dot C power 2 by 5 power 5 by 3 into Z minus Z naught power minus 5 by 3 into 25. That is the equation. Similarly, U, you can see that it is Q dot C power 1 by 3, very simple correlations, into Z minus Z naught power minus 1 by 3, where the Z naught itself can be calculated as the total heat release with the total heat release in kilowatt. Okay. So you have to differentiate here. Q dot C can be 60 to 80% of the heat release rate, which is Q dot, total heat release rate. Now again, McCaffrey in 1979 has given a correlation considering no virtual origin, where some constant, you can see the constants vary between say these two, say Zukowski and this. Some improvements have been done between the McCaffrey and Zukowski. The constants are slightly varied, but the overall variation trend with respect to Z will be different. That's it. Similarly, if you go for Kung et al., you can see that some virtual origin is used. Also, a factor called Z star is also used. That is distance from the top of the fuel surface. Z00 here is the average height. Okay, so this is somewhat more complicated expression, where more with respect to the distance or the virtual origin is considered, but virtual origin itself is correlated with respect to heat release and a factor called Z00, which is the average height. But this average height varies as 1.6 for 2 tire or 2.4 for 3 tire and 4 tire cases, because there are multiple, maybe it is in a multiple multiple layer fuel layers here. So lot of several correlations are available in the literature, but you can see that the simplified analysis, which has given the trend, like delta T varies as Z power minus 5 by 3, U varies as Z power minus 1 by 3, and the radius varies as Z. Those trends are preserved in these correlations. Now let us go to the air entrainment rate. Air entrainment rate, we have seen that when you consider a control volume here at a particular height, so this is a dz at a particular z. Now air comes in with a velocity of v, what we have taken as alpha times u, where u is the average plume velocity at a particular height. So the idealized plumes, the air entrainment into the plume was assumed to be alpha, which is a constant, into u. Okay, now we can consider the air entrainment in this manner, that is the mass flow rate of entrained air, m dot ent, equal to some constant, which is a non-dimensional constant, E into rho infinity pi b u square into u naught. Okay, now what is u naught? U naught is the center velocity. At a particular height, and the bu is the plume radius which is got from the velocity profile. Okay, so this is u naught, and the radius at which u naught drops to u naught by 2, that is taken as, this distance is taken as bu. Based upon the velocity profile, the plume radius bu is estimated in this and used here. So rho infinity area pi bu square into u naught is center velocity, that is the what mass flow rate of the plume, you can say. Now E is the non-dimensional constant. Do you understand? Now how will you calculate bu? Again, velocity measurement is normally very complicated. So you can say that value of bu is evaluated using the expression for bt by setting t naught by t infinity equal to 1. Do you understand? So if you do that, then I can get the value of bu. So the expression for u naught using this bu or bt and the expression for u naught, I will get the mass entrainment rate as this. Okay. So go back, you see here. Okay. From a simplified analysis, basically what I am trying to do here is I calculate this particular expression based upon the expression for u naught. Go back, I will show the expression again here. From this expression, from this expression as well as from the, so substitute this expression for u naught here. Bu, you can use the expression for bt, which is there here. This is the expression of bt, but just set the value of t naught by t infinity as 1. So what I am saying here is bu will be equal to bt calculated by taking t naught by t infinity as 1. That's it. So that you use. So we have expressions. In this mass entrainment, you have bu term. The bu term is calculated from bt term. bt is calculated using this expression for the improved Plume solution, which is there here. From here, t naught by t infinity set as 1. So bu will be equal to 0.12 into z minus z naught. Similarly, u naught expression is given here. You use this expression and get the expression for the mass entrainment rate. Do you understand? So instead of just taking some alpha into u, this will be valid only when you take an average velocity or a top hat profile. Instead of that, I consider a expression like this, where the mass entrainment rate depends on the mass flow rate of the plume, and there is a empirical constant, non-dimensional constant. Now in this expression, I have bu. I have expression for bt. So bu can be calculated using the expression for bt, but setting t naught by t infinity as 1. Then I have an expression for u naught from the improved Plume solution itself. By substituting these two, I can get the mass entrainment rate as E, non-dimensional empirical constant, into G rho infinity square q dot C by C p t infinity whole power 1 by 3 into z minus z naught power 5 by 3. Okay. here this expression BT expression, and this if you use you will get this. Okay. So this is the now what is the value of E? So E it all reported E as 0.153, but later it was actually changed to 0.24. But please understand that there are this is empirical value, but what is QC? QC is now taken as 70% of Q dot. Q dot C is taken as 70%. So as we told earlier, it may be 60 to 80%. So by taking QC as 70% of Q dot, E was proposed as 0.24 by the literature. Okay. So this is a expression which will give you the air entrainment rate in the Plume region as a function of Z, again which is dependent on the heat release rate. Now some more expressions which are more and more complicated is there. See, for example, we have this expression here, some term, extra term is added because of, see, when you do more and more experiments and try to measure the air entrainment, some type of empirical correlations we can add. Escalade in 1986 improved the previous solution which is given in this here, this previous solution to this by adding one more factor here. You can see that there is one empirical constant and he introduced another empirical constant G, all others are known here. So this, when you add this term, you will see that the entrainment rate is, see, finally if you measure from the plume using a hood the mass flow rate of the product gases, you know what is the mass flow rate of the fuel, you will easily understand what will be the entrained air, total entrained air. So based upon that, you can correlate this. But this has two empirical constants here, but the same trend basically. When you do this curve fitting, E was suggested to be having a value of 0.196 and G is 2.9, and this expression with these two values are able to estimate the mass entrainment rate at and above the mean flame height, at the mean flame or above the mean flame height, closer to the experimental data. Okay. So this is the important thing, mass entrainment rate, another characteristic of the plume. So in the plume, what we desire is to have the variation of the plume radius. So BT was found, variation of the plume velocity. So U naught center velocity with Z, and then you can give a Gaussian profile because you know BT now. So Gaussian profile says that it is the center velocity will be higher maximum and it goes to 0 at the radius. You can do that, or you can say the radius at which the velocity or center end temperature or center end velocity drops to half of the value. So BT and BU can be taken. Then delta T variation also was seen. Now another important characteristic is the entrainment of the air in the plume region, that is also correlated with experiments. Okay, now under atmosphere, so this is the correlation given. Now some more improvements have been done here. So under atmospheric conditions, using the above values of E and G. So when you take atmospheric conditions as say some T infinity value, some Cp value, so there are some lot of constants here. You can get rid of them and put some numbers. So you know U equal to 0.196, G equal to 2.9, but give a value of Cp, say maybe 1 kilojoule per kg Kelvin, T infinity 300 Kelvin or 298 Kelvin, G 9.81. So rho infinity again can be say 1 kg per meter cube and so on. When you substitute these values for atmospheric conditions, that is ambient conditions or standard ambient conditions, this correlation can be simplified as a correlation like this. That is, it depends on Q dot C, so 0.071, Q dot C power 1 by 3, Z minus Z naught power 5 by 3 into 1 plus 0.027 q dot c power 2 by 3 into z by z naught power minus 5 by 3. That is it. So, this is the correlation which takes into account of virtual origin and gives the entrainment of air at every z as a function of height. Now, further simplification were done at the mean flame length. So, please understand that the previous correlation holds good at and above the mean flame height. So, for example, if there is a source, there is a mean flame height like this, at the mean flame height or above. So, Z starts from the mean flame height only. So, now again at the mean flame height, the correlation can be expressed by considering delta T as 500 Kelvin. Just at the flame height, mean flame height, T at the center line minus T infinity, if it is taken as 500, then the correlation can be written as m dot ENT will be equal to 0.0056 into q dot c. That is it. Now, several based upon the experimental results, several correlations are also given. For example, for fire diameter of 0.3 meter or higher than 0.3 meter, within the flame zone Z less than or equal to HF, within the flame zone, a correlation is given as m dot ENT equal to 0.0059 q dot c into Z by HF. Okay, this works within the flame zone. Now, one point to note is in these cases we are using q dot c, that should be in kilowatt. Q dot c is the convective heat flow rate, that should be in kilowatt. Length dimensions are in meter and the mass entrainment rate in kg per second. Okay. Now, all this we have used correlation for strong plume. Okay. In general, fire with much lower HF by D ratios have not been studied. HF by D, if it is very low, okay, then that is, for example, very big pool, the HF by D will be very low. In those cases, we cannot straight away use these correlations because there is no experimental support for this. So, when you want to use for such cases, we have to apply some caution. Okay. Now, I have shown some experimental results of a flame. For example, it is methanol pool of diameter 6 centimeters, and at different time instants I have shown the flame shape or a photograph, and the flame heights visually observed is also put beneath this. There is a clear fluctuation. You can see that flame height is 14.26. At another time instant, maybe regular time instant, it is increasing to 18, then it drops to 8, then it again increases to this, and this cycle continues. There is a fluctuation. So, that is what? So, there is a constant zone. There is an average flame height for this, obviously. If you take more time and take a average, then you get an average flame height, and there is a maximum flame height, which is actually the boundary of the intermittent zone. So, the flame pulsations results from air entrainment. Okay, you can see this clearly. So, here the air entrainment is starting. So, the flame radius also is somewhat higher. When the air entrainment comes in, the flame is actually becoming narrower here based upon this. See this and see this diameters. Now, you can see this, the air is actually able to entrain, chopping off this flame, and the flame height reduces suddenly to this value. So, as the air entrains, the flame tries to grow, and it actually reduces the radius. The airflow from the periphery reduces the radius, and this flame goes off and chops off this. So the flame actually forms like this here, and again the flame grows slowly and reaches this. This is one cycle basically. So reaches, so between these two, this cycle will be complete. So we can see that the growth, shedding off of the flame tip, again smaller formation of a smaller flame, and its growth to again a bigger flame, etc., is observed in several experiments. Basically, this is a case where the flow is not much turbulent because the diameter is about 6 centimeters. Now, that means when you plot HF versus T, there is oscillation, something like this. Now, I can convert this into frequency. The time history, the time domain can be plotted as amplitude versus frequency. So now you get something like this, a frequency. This is the frequency of the oscillation. There will be multiple frequencies also. I am saying some dominant frequency will be there. So this dominant frequency of this oscillation, they are actually obviously multiple frequencies like this because of the multiple oscillations here. So now the dominant frequency is correlated as a function of the fire diameter. Sarijan and Ahmad has done in 1993 by considering fires of diameters 0.03 meters to 20 meters, and they say that the frequency in hertz will be 1.5 divided by the diameter in meter power 0.5. So if you see that for smaller pools, the oscillation frequency will be higher. Now, now we can see that there is a fire in a enclosure. Fire can happen anywhere. Okay, so for example, if there is a room and center of the room there is a fire, there will be no interaction with the walls, side walls. Okay, there are 4 side walls. There will be no interaction because it is in the center. The walls are much away from this particular source. Okay, so for this fire, actually it grows as an open fire until it hits the ceiling. Based upon what is the height of the ceiling from the floor, the plume travels certain distance and hits the ceiling basically. Now, if you go to a corner and there is a fire in the corner, then the plume can straight away start interacting with the side walls. Okay. Now, the interaction of the side walls will be there, plus as the plume goes and hits the ceiling, again the interaction of the plume with the ceiling will be there. That means in all the cases, in a compartment fire or enclosure fire, the interaction of the plume with the ceiling is extremely important. Okay, so several researchers have investigated the effect of interaction of the plume with the ceiling. Okay, so you take this is ceiling here, this is ceiling. A fire comes and the plume starts and grows like this, and it hits the ceiling basically. Then after hitting the ceiling, the fire actually goes parallel to the ceiling. Okay, so the plume rises vertically, buoyancy forces aid them to rise vertically. So that is why the interaction with the ceiling becomes more and more important. Then it impinges with the ceiling. So in the corner fire, etc., the side wall may interact, but since the buoyancy force is predominantly vertical direction, the side walls may not affect the propagation much. There will be some interference effect, that's fine, because what basically happens is if there is a center fire, then the entrainment of the air occurs almost uniformly through the fire from all the periphery. But if it is going to be a corner, then the side wall will restrict the air entrainment, and the air entrainment will asymmetrically occur from one of the open sides. But in this case also, the ceiling interaction is extremely important. Okay, so the plume rises vertically, impinges on the ceiling and bends in the perpendicular direction, that is perpendicular direction to the plume, or it may go parallel to the ceiling. Movement of the plume after impinging the ceiling, okay, now it goes like this. It changes its direction perpendicularly and goes parallel to the ceiling. The movement of the plume after impinging with the ceiling is called ceiling jet. Okay, ceiling jet. Now, please understand that normally in an enclosure or a compartment, we put the sensors like CO sensor, heat sensor, smoke sensor, etc., which are used to detect the fire, is put in the ceiling. So that means the ceiling jet, the smoke goes to the ceiling, because in between there we cannot put any sensor. So it goes to the ceiling and spreads on the ceiling as a ceiling jet. Now, the magnitudes of temperature and velocity of the ceiling jet will be very important for us. Why? Because we put our fire safety devices such as smoke, heat and heat etc., which will actually trigger a sprinkler etc. into ceiling. So now the ceiling jet is strong enough, the magnitude of the temperature and velocity of the ceiling jet will be higher. That means that the detectors will be able to detect the occurrence of a fire by sensing the temperature etc. of the ceiling jet. So the ceiling jet is very important to understand. So what are the characteristics of the ceiling jet? Now, interaction of the plume with adjacent walls or corners are relatively not very significant. Why? Because as I told you, the plume actually rises up. Only main thing what the corner or side walls can cause is some asymmetric air entrainment. But the strong influence is by the ceiling. That is, the plume interacts much and more uh, strongly with the ceiling rather than the side walls and the corner. So this is the schematic of the ceiling jet flow. So let us say there is a ceiling, there is a floor, and there is a ceiling at a height h, capital H, from the floor, and there is a fire source which gives a heat release rate of Q dot. The plume generates from the fire. So this is the velocity profile or temperature profile of the plume, and after hitting the ceiling impinging point, it actually goes parallel to the ceiling. That is, the plume direction changes perpendicularly and it goes. Now, this layer has a height. So, after a particular time instant, this layer has a height of LT. Okay, now if this jet cannot go out, then this layer will descend down. If this can go out, then it may be a steady layer of steady constant thickness. For example, if there is a window here or a ventilator here from which this can go out, then obviously this layer, if there is a continuous fire, this layer can become steady layer. If it is not, then the layer can descend down. That is, the LT, okay, can basically increase. Okay, now within the ceiling jet, I draw the velocity profile like this. Velocity is very low, goes to 0 at the ceiling, no slip condition, and it increases to a maximum at a particular distance from the ceiling and goes to again a 0 value asymptotically at the end of the layer. Temperature based upon the wall temperature, because the wall is being heated by this. Based upon the wall temperature, the temperature will be here, and at a particular distance, the temperature of the ceiling jet becomes maximum. Then it asymptotically reaches the temperature here. So this temperature is ambient temperature because of the location here. If you go to this location, for example, and draw, then the T infinity here will be higher because it is close to the flame. So you can see that this is the schematic of a steady. I am saying steady means I am allowing the fire is steadily burning, and the smoke or the hot gases go out. So, there is a definite thickness for the ceiling jet, which is formed from the ceiling, which is at a height of h from the floor, and the fire has a q dot, heat release has a q dot. Okay. So, how to find these profiles? Magnitude of this, how to find? That is the thing. Again, correlations have to be used.